Lecture on ML Type Inference. This is video number 9. In this video, we study a type system lambda def for top-level let declarations. We start by analyzing type inference problem of lambda let, which is the Damas-Milner type system for ML. First, we review type inference problem. As we have learned, the general form is to determine this set of all possible typing derivations, right? So if we can solve this general form, we can solve the other forms of type inference problems as we have learned. And for lambda terms under a simple type system, this general form of type inference problem is solved by computing a principal typing of an expression, right? So far we have learned, right, in detail with the completeness and the soundness of type inference algorithm. However, in the Damas-Milner system for ML, this system, a typing is in general of this form, where you have a sigma type inside of environment, where this sigma denotes types possibly have a for all bind. Type variables are for all abstracted, right? So in this type system, an expression does not in general have a principal typing. To see this, examine two simple typing derivations. Take just for very simple case for variable x, and consider this typing and this typing, right? This typing under this environment x of type t, under this environment x has type t. The other one, under this environment x of type for t dot t, x has type for t dot t. Both are obviously derivable typing. Unfortunately, neither of them represents the other, and indeed there is no typing that represents both of them. So from this observation we know that it is difficult to solve the general form of type inference problem of this Damas-Milner system. At least we can't apply for lambda expression case, that PTS. We can't apply that strategy to computer principal typing, because there is no such thing in this lambda let system. So this is a problem that makes type inference problem of ML complicated. Now our agenda is to track down the origin of the difficulty or complication of ML type system. For this purpose, we examine semantics of the let construct, which makes ML polymorphic language, right? Just for the purpose of explanation, we redefine the set of ML expressions as the set generated by this BNF notation. The difference from the previous definition or standard definition is that we distinguish between lambda variable and let variable, right? But I note that no restriction is introduced by this distinction of x and large X, lambda variable and let variable. I also note that in the original paper by Milner, he defined a type assignment system where notion of prefix syntactically distinguish between two prefixes, two binding, lambda binding and let binding, right? So this is just a note. So I repeat that there is no restriction. So you get the same language. Now, the reduction rule that determines the meaning of let construct is formulated by this rewrite system. So this let expression rewrites to this expression where this is the result of substituting x with E1 in E2, right? So formal parameter name of this expression is replaced by the body. Body means this expression, right? So this is a standard rewrite rule. So this is equivalent to this beta rule, right? So beta rule. So that so this red construct can be represented, as far as meaning is concerned, can be represented by this combination of lambda abstraction followed by application. So that apply this function to this argument, you get this result by rewriting of the lambda calculus. This is called the very basic beta reduction, and therefore, as far as semantics is concerned, this red construct is redundant. So ML introduced some redundant notation, redundant construct inside of the language, which is kind of alarming, right? So if we have something primitive, and then if you have also introduced some compound rule that already definable and using primitive, then you must be very careful, or something going wrong easily. The purpose of introducing the redundant red construct that is equivalent to this compound term, the purpose is obviously to have a more powerful typing for this binding, this variable binding. So in order to analyze this property, we analyze basic property of this typing under the simple type system. So this term, in order to have this term, we must have this compound derivation. So this term, typing of this term, is a composition of this abs rule and APP rule, abs rule and APP rule combined, right? So, and then result is that assuming under this gamma extended with x colon t1, under this environment, E2 has type tau 2, and also E1 has under same gamma, E1 has type tau 1, then this compound term has type tau 2. So this is a compound rule or compound derivation, obviously, the basic standard derivation. In order to have this term, we must have this derivation. This is the first observation, first property to note. The second property is this one. So beta rule we saw in the previous slide preserves typings, meaning the following. If we have this typing derivable, right, so this compound term has typable, then the same typing is also derivable for the result of rewriting of this term, right? So this is the basic property we need for any sensible type system. And of course, the simple type system, we have this property. This property is called the subject reduction property. However, the converse does not hold. Converse means that this implicates the reverse of this implication, so that in general, if we have this derivation for this term, that is a result of beta reduction, does not imply that the original term has the same typing. So this happens. This means that this is derivable and this is not derivable. This happens in the following two cases. First one is that E1 does not have a typing, or E1 contains type error. Still, this derivation can be possible because x may not appear in E2. In that case, this term doesn't contain E1 at all, right? So this can be typable even if E1 is not typable. This is the first case, one case. But so this is typable, but this term has explicitly inside of this term E1 exists as a subterm, and E1 must be type checked in this derivation. So this can't have a typing if E1 does not have a typing, right? Second case is that X occurs more than once in E2, right? In this term, E1 occurs two different places, and two different places have different contexts, and therefore E1 can have two different typing derivation. While this one, E1 has only one occurrence, and therefore E1 has only one typing. And this tau1 is fixed, and that is a type of the variable x. So this is more restricted than this one. So these are property. These are three property in the simply typed lambda calculus, right? So with this background, we now analyze typing rule for let expression in this Damas-Milner system. The rule is this one, right? So we have seen this rule before, of course, right? So for this let expression to be typable, type tau2, then the condition is that E1 must have some type tau1, and E2 must have some type tau2, which is the same as the resulting type, under the assumption that this let variable x has type tau1, but some type variables are abstracted. Those type variables that doesn't appear in the rest of this type environment gamma. Right? So this is a rule, and under the knowledge about the typing derivation of this equivalent term in simple type system, we notice that this rule is a special treatment of this composition of absent APP, which can be summarized by this way. This is a summary of the derivation we have seen in the previous slide, right? So the similar, but the difference is that we, in this simple type discipline, we do not do this type variable abstraction for this tau1 of this type E1, type of this expression E1, right? So this let rule is more powerful compared to the equivalent case in the simple type discipline. So in order to have this extra power, ML introduced this let, in some sense redundant term, but a special treatment in typing, right? So this is the essence of ML, one essence of ML typing. Now, the same effect of this let rule is achieved by the rule, non-standard rule of this rule. I call subst. This rule, in order to have this let expression to have some type, E1 must have some type tau1, right? Because otherwise this entire term has a type error. So this must have some type. And also this result type is a type by expanding this E2 with this definition, that is this one. That is the result of rewriting this let expression, so that substituting occurrences of x with E1, and then we have expanded term here, right? So later we show that type system with this rule and type system with this Damas-Milner style let rule are indeed equivalent, but this equivalence proof is rather complicated, rather elaborate one. We will come back to this point later. For now, we make two comments, or this may be a warning, right? First one is that special treatment of some particular cases make system complicated, particularly inductive reasoning difficult. And the second comment is that introduction of a non-standard rule, this rule, must be done with care. This rule is potentially dangerous, right? Because this term may be strictly bigger than this resulting conclusion, right? So sub-derivation differ to a derivation of a bigger term. That may be usually dangerous. So we must be very careful in defining this rule. You can't say that this is just a macro expansion. No, macro expansion can't be in general make a decent type system. I will come back to this point later. Right? So at this point, these are just a comment or warning. With analysis of let rule in Damas-Milner system and the corresponding typing derivation in the simple type discipline of the lambda calculus, we now make some high-level analysis of ML let typing. That is this one, a polymorphic part, which is at this point ambiguous and intuitive way of saying, but let's go on. A polymorphic type of a let variable type is given by a principal typing of the corresponding expression, as shown in this example, right? So we have principal typing for this identity, and then using this identity term in let expression. The let expression has type, this generic type, right? TLT, which is derived from this principal typing. And because this is a polymorphic let, this T, polymorphic part of this type of X, can be instantiated differently for each occurrence, this and this. And this small x and small y are variable whose types are inferred, right? So under this environment where you infer x to be t1 and y to be t2, and then this occurrence of this large X is used as an instance of t1 arrow t1, and this occurrence is used as a term of type t2 arrow t2 and resulting in this type. And this blue part, which comes from this principal type of this term, is not subject to type inference. So now this is a kind of high-level intuitive, at this point, way of observing this, what is going on in that expression. And let's continue in intuitive analysis. So that is the following. If we can somehow separate polymorphism of let variables from typing, then we can extend PTS to let construct. Right? This separation is easy for closed expression such as this one, right? So closed expression. So in this case, we can make this compound term, right? We have a declaration of variable, let variable, under this declaration of let variable, this term. So declaration paired with term. This compound term with declaration has this type under this environment assumption, right? So this type is closed because term is closed. Therefore, type, derived type, is closed, right? So we don't have to infer the type of this large X. So this is what I mean by separation. However, let bound expression contains free variables, as in this expression where this this expression, which is bound to this large X. This X is free, so that this must be the term to be inferred. This must subject to be inference, type inference. So you need to infer the type of this X, and type of this small y, and type of this small z. Right? These are ordinary variable, free variable, and therefore must appear inside of typing environment, assumption part. Right? But so this large X, the type of this term, this X part is you need to infer and appearing in the type environment. But the rest of this W part, or I appeal at this moment to intuition, right? But let's go on. These intuition will become clear and rigorous later during this video lecture, right? So now this type of X is intermixed with derived polymorphic part and monomorphic type part, which must be inferred. So for this case, where let bound expression contain free variables, some further additional machinery is necessary. So this is a summary observation of the Damas-Milner system lambda-ret for ML. First one, rules for APP and APS are restricted to monotypes, and therefore derivable typings of lambda terms are the same as those in this simple type discipline, lambda. Second one, a polymorphic part of sigma in let construct. The type of this let variable is given by the expression, the corresponding expression, this expression, and is not subject to type inference. Third, when the body E of let definition is restricted to a closed term, then the necessary typing machinery mechanism is similar to built-in primitives such as map. So this is built-in primitive, where built-in means closed, and therefore typing contains no free type variable. Typing is completely closed, independent of rest of type inference, rest of type variable. There is no interaction. So these are three basic observations about the Damas-Milner type system for ML. So from the above observation, we come up with a new strategy for ML type inference. First, define a type system lambda def for closed top-level let definitions and construct an algorithm PTS def to infer a principal typing, which is a straightforward extension of PTS. The second, define a type system lambda ML for ML by translating this system ML to this lambda def, which is a restriction that let expression, let definition must be top level. Third, prove the equivalence of lambda ML and lambda let, namely this proposition. If something is derivable under this definition obtained by translation, then if and only if the same typing is derivable in the Damas-Milner system. If we can complete all these three steps, then we have a new type inference, which is significantly simpler and easy, more systematic to reason about type inference process and type inference problem. Right? So this is a strategy we are going to take. The first step of developing this agenda is to define a type system for closed let definition I call lambda def. So term and type the same as before about term expression. We make a distinction between lambda variable and ret variable, but this doesn't make any effective or any distinction, any restriction, and we have monotype. In addition, we define type schemas and ret variable declaration and terms as follows. Type schema, we use this notation. This bind or mark all the type variables in tau. Ret variable declaration delta, this is an environment of this form. So this is a declaration inside of program, or you can regard this way. So for each ret variable declared a corresponding type scheme. And then term, which is a pair of delta and E. So this is a term of this calculus. So typing of this lambda def is of this form. So this declaration expression with declaration has a type tau under this gamma. Gamma is just a map from a finite set of variables to monotypes. Right? So now new ingredient to this delta can be interpreted as a model of the usual assumption of polymorphic primitives, such as map. Right? So there is no difficulty in introducing polymorphic primitive. So that a polymorphic primitive is not subject to type inference. Just assume that map has this scheme, and then whenever you use this map, you make an instance. That is a polymorphic primitive. And this introduction does not complicate the type system. We will see in the following steps. So in order to complete the definition of this lambda def, we must specify the set of typing rules. Here it is. First, we have two notation. One is this fresh inst of type schema. This is the type obtained from tau by substituting its type variable with fresh type variables. And then this relation, some type, is an instance of this type scheme. If this fresh inst, there is some substitution that equate this fresh inst and this type tau prime. Right? So this corresponds to usual notion of type instantiation relation. Using this notation, we define typing rule. First four typing rules are the same as in the simply typed lambda calculus, except that each expression has tagged with declaration delta. But delta doesn't have any impact, any interaction. So this delta is just there, just keep delta. Right? So otherwise this expression part is exactly the same as before. So this value under x colon tau, x has type tau. This is a constant. And this is abstraction. And this is application. It's exactly the same as in the lambda case. And then we have two additional rules for ret and ret bar. For this ret expression to be typable, to have a typing, then E1 must have some type under this empty assumption, empty type environment. This force, this declared expression to be top level, right? So empty means that you can't be any free variable, right? So this is top. This must be a top level, the same as primitive or built-in primitive. So this is one condition, and the second condition is that because this under this empty gamma, then tau 1 is conceptually closed polymorphic type. So we mark all type variable in tau 1 and put it in this assumption declaration part in this term and type check E2. And that succeed with some type tau 2, then the result of this type. So this is the rule let, and let bar is this rule. In order for this let variable to have some type, this must be declared in the term. Then the type is the instance of this declared type scheme. So these are additional rules. Now you can see that this is a natural extension, or natural simplification, you would say, in the Thomas-Milner system. So we write this way if this is derivable in this type system using these rules. Right? So this is the definition of lambda def. So we are ready to define type inference of this lambda def. Actually, type inference of lambda, simply typed lambda calculus, straightforwardly extends to this system. We only have to do the following. First, we define the notion of principal typing, which is this one, which is exactly the same as before. This typing is a principal typing of this term if it satisfies this equation, right? So this left-hand side is a set of all derivable typing. The set of all derivable typing is equal to this set. This set is a set of all instances of this given typing. So this is the same notion as before. It is the principal typing that represents exactly the set of all derivable typing, and principal typing does exist in this lambda def simply under this definition. And then we need two things. First one is to define a type inference algorithm as a function of the following form, taking an expression, return gamma and tau. And third, of course, we need to prove the soundness and completeness of this new type inference algorithm, which we now term. So type inference algorithm PTS def of lambda def, as I said, it straightforwardly extends. So let's see this, right? So first rule, four rules for definition of PTS def for expression of lambda expressions are exactly the same as before, right? So we skip reading this part. So you only have two new definitions. First is let, second is this x, let variable. Let's see first this let case. So this is the inference step for this let expression. First you apply this PTF def for this E1, right? And we get, if we get this typing, then do the following. If this gamma is non-empty, then failure, because this system requires to be a top level, no free variable inside of this term. So if gamma is not empty, then failure. Otherwise, just return the result of inferring E2 under this extended declaration part, extended with x colon for marked tau 1, which is obtained by this tau 1. This is just simply use this tau 1, but all type variables are marked, right? Simply as this one. And for the let variable x, you check that this x is in the domain of delta. If it isn't in the domain, then failure. Otherwise, make a fresh instance of the declared type scheme. Right? So this is the definition. I would say straightforward, which I hope you agree. We have now completed the 2 steps out of 3 and the remaining 1 final step of soundness and completeness proof of PTS def. right? So soundness of PDF def case of variable x, net variable x. The theorem, soundness theorem, states the following. If PTS def of this term returns typing, then for any substitution S and any type environment gamma such that S of gamma E is contained in gamma, this typing is derivable under this type system. So as you can see that this statement is exactly the same as before in the case of simply typed lambda calculus. Of course, the difference is this existence of this declaration part, but otherwise it's the same shape, right? So proof is by induction on the structure of this expression E. And as you can see that from the definition of lambda def, whose lambda expression parts are the same as before. Therefore, the cases other than x and let are the same as those of this lambda, simply typed lambda calculus case, the case of the plain PTS. So we show the case for x and this let expression. So here is a case of x. So this is a comment, as before, comment. X is type checked this way, and the definition of PTS def for x is this way. Now, and we need to show that so any S and gamma containing S of gamma E, this we need to show this is derivable. So for this purpose, we suppose that this PTS return this gamma E, gamma tau E, this pair. Then by the definition of this PTS, this delta must have this shape. There must be some x in the domain of delta. So delta must be this, containing this x part. And returned gamma must be empty because of this definition, right? Always empty. And tau E is a fresh instance of this type scheme. Now we need to show that this part. So for this purpose, we let S be any substitution and let gamma be any type environment. Right? Any type environment containing empty set is simply any type environment. So by the definition of fresh instance of this type schema, this relation holds. Then by the rule let bar, this derivable. This is actually trivial, but just write down in detail. Right? Soundness of PTS for the case of let expression in this case. Now this is a comment, so that let expression has typing in this way. So this is a rule for let typing, and this is the definition of PTS def for let expression. And we need to show that this is derivable in the case of let expression. So we suppose that this succeeds. Then by definition of this algorithm, this E1 must also succeed with some pair with empty type environment and some type tau 1, right? And then also this E2, PTS def of E2 must also succeed with some pair gamma E and tau E under this extended declaration. So now by induction hypothesis, this E1 has typing, right? We take empty substitution in this case. So by the induction hypothesis applied to E1, we have this one. And now for the rest of the derivation, this part, we need to show this part. We take arbitrary substitution S and gamma such that S of gamma E is included in this gamma. By the induction hypothesis applied to E2, we have this typing derivation, right? So by the definition of lambda def, now we can conclude that this is derivable by the rule let, right? So this completes the soundness of PTS def. Nothing difficult, just a straightforward extension of PTS, as I said, right? So this concludes the proof of soundness of PTS def. So this is the final piece of the development, that is completeness of PTS def. The theorem is the following statement. If this typing is derivable in this type system, lambda def, then PTS def succeed with typing such that there is some substitution S that applied is returned. The environment is a subset of this given gamma, and S applied to return tau E is equal to the given tau, right? So again, this statement is the same as before in the case of simple type system of lambda expression. The proof of this completeness theorem is by induction on the structure V. Again, from the definition of lambda def, the cases other than x, large X, and less let expression are the same as those of lambda case. So we show first the case for let variable x. These are comment, right? So x is type checked by this rule, and PTS return this way. So to show the conclusion of this theorem, we suppose that there is a given typing derivation for this x. Then by definition of the type system, this delta, given delta, must contain x component of some type scheme. And this tau, derived tau, is in the relation of this, namely the instance of this type schema. So that by definition of PTS def, right, PTS def of x is the fresh inst of this type schema, which is assumed to be in this delta. So by definition of this instance relation and this fresh inst, tau is a result of application of some substitution S of this fresh inst of this type scheme. Also, this S applied to empty is contained in delta by trivial definition, so we completed this case. The proof of completeness of PTS def for the case of let expression, right? This case. So these are comment again. And now in order to show the concluding part of this statement, we suppose that this expression, this term, has some typing tau. So that by definition of this type system, because since this has a typing, then E1 has some typing tau prime under this empty gamma, and E2 has typing of this tau and same gamma with the extended declaration with declaration gamma delta extended with x of tau prime, type schema tau prime. Now, by the induction hypothesis applied to E1, PTS succeed with some typing such that this tau prime is obtained by substituting this obtained tau 1 with some substitution S1. And then this type schema tau 1 and type schema tau prime stands in this relation, which is defined on the next page, and then by lemma stated on the next page, this derivation is derivable. So by the induction hypothesis applied to E2, we know that this PTS succeeds with typing. But since this type inference algorithm returns the same as this is just a tail call, so returns the same thing as for this E2. And therefore, we have completed this case for this let, and therefore completed the theorem. Alright, so remaining piece is this lemma. Right? So we now show finally this lemma. We call weakening lemma on the next page. The remaining piece is this weakening lemma of lambda def, this type system. So for this lemma we use notation, right? So this type schema and this type schema is in this relation that this is bigger than this one if this smaller instance, fresh instance, is obtained by some substitution applied to this fresh instance of this bigger instance. Intuitively, this corresponds to this type schema is more general than this one. And then lemma says the following. If we have a typing derivation with x of this, with the assumption x in this declaration part of some type schema, and there is some bigger type schema compared to this type schema, then you can replace this type schema with this bigger one, and still we get the same typing derivation. This is intuitively clear that because you strengthen the assumption part, declaration part, with more powerful polymorphic types, and therefore the same conclusion should be obtained. Because you can strengthen the assumption, you still get a result. That is called weakening, because something you strengthen in the assumption part, then the statement gets weaker. Okay? So this lemma is a usual lemma, that if you have a statement, then something weaker statement can also be proved. Right? So proof is by induction of the structure B. For this proof, we suppose some derivation with the declaration of x, and this relation, the bigger one, exists for this declared type schema. And then do case analysis. Cases other than this x are immediate consequences of the assumptions or induction hypothesis, nothing to be proved. The only case to be proved is this let variable x. So this is a comment. So in order to show that this replaced derivation is derivable, right? So by definition of this type system, so this tau, first of all, the given derivation, there is some substitution s, and the result is the substitution of this fresh inst. So by the definition of this relation, given assumed relation, this equation holds for some s prime. Then this equation holds, and therefore this tau in the given derivation is an instance of this bigger type scheme. Then by the rule let bar of this type system, we have this derivation as desired. So this completes everything, every step, every detail, including trivial steps in the development of lambda def, which is a lambda expression extended with top-level polymorphic let construct. So the reason why we go through in every detail is to verify that nothing is complicated, just a simple and mechanical step to extend given the basic type inference system for lambda expression, right? Therefore, so I hope that you understand this simplicity and easy to understand way, and the proof is also nothing complicated. Therefore, compared to rather elaborate and rather complicated proof of algorithm W and the corresponding lambda rate, this formalism, if we can further extend to generalize full ML, then we should say that this is much superior because of the simplicity. Usually, simple formalism to show the same desired property is obviously superior. So that is a message of this today's lecture, and now we completed the first part of the development of ML, new formalism of ML type inference. We end this lecture by summarizing this lambda def. The type system of lambda def, which is in this type system, polymorphism is restricted to top-level closed declarations. And typing derivation is equivalent to simply typed lambda calculus, system lambda, extended with built-in polymorphic primitives. As in this simply typed lambda calculus, the notion of principal typing is naturally defined. And about algorithm PTS def, this is a straightforward extension of PTS for lambda, and has this desired property. If PTS def returns some typing, then this is a principal typing of a given term in this type system. And if PTS def return failure, then this term has no typing in lambda def. So for this type system and the language with top-level closed declaration, we have solved type inference problem completely with a rigorous proof of completeness and soundness of the algorithm. Now, this is the end of the lecture number 9.